Hi, Mrs. Melchetter here with part C of our notes on chemistry. Okay, so we left off in part B with what bonding was, which are when electrons are either shared or transferred to complete that outer shell. So that first inner shell, remember, wants to have two, and then the outer shell has multiple levels to it, but in all, that second one wants to have a total of 8 with all of its different levels. And so for the elements that we're going to be looking at, like up to carbon, nitrogen, oxygen, we want to focus on what's going to get their outer shell up to that complete 8 that they would like. Okay, so when two atoms share a bond, or they create a bond where they're sharing those electrons, that's a pretty strong bond because, when you share something with somebody, you create a bond with them. So they share those pair of electrons, and the atoms will be held together because those electrons are going like this, and they're you never know where they are. They could be with the hydrogen, they could be with the oxygen. Okay. So, or the carbon, or wherever. They are all over the place. So that creates a stronger bond. Sorry. There's, you can have a single bond, so like hydrogen to hydrogen, where they're only sharing the one pair of electrons, or you can have a double bond, like in oxygen to oxygen, where there's two pairs of shared electrons. And these usually occur between nonmetals. We don't need to worry so much about that because, again, like I said, we're going to be focusing on that CH and O and P the most. So atoms sometimes will be attract those shared electrons in varying degrees or different amounts, and that's called electron negativity. And so some atoms are more electron negative, and so they're going to have a stronger attraction. So think about it like they like those electrons. They want those electrons. So they're going to be pulled closer to those atoms. Okay. If we end up with an equal attraction, like two hydrogens, well, they're the same thing, and they both have the same electron negativity. So what they will do is they'll have an equal attraction, and they'll pull on those electrons equally. So we call that a non-polar covalent bond. So it's something that's non-polar. Usually non-polars are hydrophobic. They tend to stay away from water. Okay. And then if you have an unequal attraction, we call that a polar covalent bond. And a polar bond, that's where one of those atoms is just a little bit more electron negative, and it will want to have that electron just a little bit more time than the other atom of the bond. So you end up getting an unequal attraction, and it kind of skews the shape a little bit. Like if you think of water, most people compare it to like Mickey Mouse ears, or Mickey Mouse with his ears. So you get that where oxygen is sitting down a little bit more, and it kind of pushes up on those hydrogens. And that is called a polar bond. And polar bonds tend to be hydrophilic. They like water, or they'll face towards the water. And that'll come important when we start talking about our macromolecules and cells and cell membranes. And then we have the ionic bonds. We do a little bit with ionic bonds, but more with the polar and nonpolar covalent bonds. So in ionic bonds, the two atoms are so unequal that one basically just grabs it and takes it off of the weaker one. And so I kind of remembered that with ionic is like, I want it. Ionic, I want it. So it like takes it from the other guy. And this can result in a positive or negative charge on one of the atoms. Okay. For an ion, when something is charged, we call it an ion. If it has a positive charge, we call it a cation. If it has a negative charge, we call it an anion. So if you're thinking about this, if you have sodium and chloride, NaCl, and chlorine is going to be the one that's a little bit more negative. It's the one who grabbed that electron and took it away. And when it took the electron away, that made sodium a little bit more positive because it took some of its negativity away. Compounds that are formed by these ionic bonds are all called salts. So table salt, which we know is a salt, but there are other kinds of salts too. And then finally, we get to the other bond that we talk about, which is hydrogen bonds. And hydrogen bonds are fairly important in biochemistry. So they are weak bonds. They're not very strong. They don't have a lot of sticking power, unlike ionic or covalent bonds. And what happens is they come from a partial charge of the hydrogen. So remember, like I gave the example of water, the oxygen is a little bit negative and it's going to pull that electron just a little bit more, that unequal sharing, which is going to make the hydrogens just a little positive. Well, those hydrogens are going to be attracted to other parts, other negative things, because it's giving them just a little bit of a charge. So one way that we can think about this is the water strider, who is able to walk on the surface of the water because of the hydrogen bonds between the water molecules. And we'll get more into that when we talk about the properties of water. And another type of interaction, which is a type of hydrogen bond, is called the van der Waals interactions. And this is when you have molecules that are really close to each other, and they kind of have these alternating positive and negative charges, which allows them to create like a stickiness kind of thing. And this is what allows that little gecko to cling to the glass. So it's a pretty cool piece there. Okay. And then what we need to also talk about is the shape of the molecule. So two atoms will often be linear. Okay, so if you have like hydrogen and hydrogen, it's going to be a linear shape because nothing is being pulled or tugged in any different way. More than two atoms, you tend to get some really kind of crazy shapes. So if you have three, it's usually not in a straight line. Not saying that it can't be, but usually it's not. And what's important about that, and as we start learning about enzymes and things, we'll see that the shape determines how the molecules are able to respond and behave. And so that's going to help with recognizing an enzyme that needs to get into your cells, or having different shapes so that you can put pieces together or build bigger molecules. Trying to talk about it without talking about it, it's kind of hard sometimes. Chemical reactions will happen when we make or break those chemical bonds. Whenever we have things that are the starting materials, we call those the reactants. That's what's going in to our reaction, are the reactants. And then what comes out are the products. And the products are kind of easy to remember because that's the ending material. And you think about a factory, it produces things. It's what comes out at the end. And so one thing that's important to remember is that reactions can only rearrange the matter. They can't create or destroy it. So if there's only 4 hydrogens on one side, you can't all of a sudden make a hydrogen on the product side. Okay. The reaction itself can look reversible, but not all of them can be undone. So what I'm saying there is that when you look at it, you can look at it from reactants to products or products to reactants, and it should all balance out, but not all reactions can be undone. Sometimes once you do something, you can't take those products apart and get back the original pieces. Okay. And so we'll talk a little bit more about balancing things when we start talking about carbohydrates and dehydration and how we put these things together. And that's going to leave us at water. And since water is a special topic in our textbook, we will tackle that in the next set of notes. Thank you for listening. And as always, please let me know if you have any questions and keep asking those good questions.